Section 1.6, Rules of Inference. So an argument is a set of statements that ends with a conclusion, which is supported or implied by other statements. We call these other statements that supported or implied premises. A valid argument is one such that if the premises are true, the conclusion must also be true. So let's take a quick look at an example. The two premises here are all squares are rectangles, and all rectangles are polygons. The conclusion would be, so all squares are polygons. An important part here is that validity doesn't necessarily mean that the conclusion is true. It only promises that the logic contained is valid. That is, if the premises are true, you will get the conclusion. But the premises may be false. This is a really common technique you'll see when people are getting in arguments or debates. You just slide in some false premises, but then you construct a valid argument, and it makes that argument hard to attack because the logic is valid. Let's take a look at an example. All polygons are rectangles, and all rectangles are squares, hence all polygons are squares. Importantly, if you didn't know anything about polygons, rectangles, and squares, and you were just giving these two pieces of information, the conclusion would be valid, even though it is not true, right? Because these are two false premises. So we end up with valid logic, but a false conclusion. Let's see how we construct one of these. So say we are told, if you live in Illinois, then you live in the US. And the fact that you live in Illinois. We want to get to a place where we can draw conclusions and say, so you live in the US. So we're going to symbolize this. I'll let I be the propositional statement, proposition that you live in Illinois, and S be the proposition you live in the United States. And this first line doesn't tell me that I live in Illinois. It doesn't tell us that you live in the US. It tells us that the implication is true. That is, if a person lives in Illinois, they would live in the US. The second line there is what tells me that I is in fact true. That is, that you do live in Illinois. So now I have these two premises that are true. You live in Illinois, and it is true, the implication that if you live in the US, if you live in Illinois, you live in the US. So we can make a brand new conclusion. From these two propositions, we create a new proposition. This three dot symbol is the therefore symbol. So we would say, therefore, you live in the United States. Provided in your notes are some is an entire table for these rules. Suggest you print this off or keep this close, keep this open on the screen as you're running through this chapter. I'll be pulling these up as we go through examples here, but as you work on your homework, it's useful to have a copy of this nearby. And you can kind of walk through them. A lot of them, you should be able to convince yourself logically that they hold up. For example, modus ponens is the one we just used. And one like addition you can talk yourself into, right? If P is true, then you can add whatever you want to onto the end of that. Right? If it is in fact a Wednesday, and I say it's Wednesday or the sky is purple, well, that's still a true statement because it is Wednesday. So when you go to work a problem, they'll start out looking like this. And here I'm giving two premises that I want to work from. I'm given P and Q as a premise, and I'm given R as a premise. And then it has this weird notation because I don't know how many steps it's going to take me, but I do want to number them. But I want to reach the conclusion P and R. So just for my own benefit, I'm going to move this down here, the conclusion, and I don't know how many steps it's going to take me to get there again, but I need to reach that conclusion. As we go through these and they get more complicated, I encourage you to keep an eye on where you're trying to go. I know that sounds like a really silly piece of advice, but when I'm looking at this, I want to get P and R. So one of the first things I need to do is I need to get P, right? I already have R as a piece on its own, but I don't have a standalone P. Can I get it? Well, I'll look through my rules of inference here. And sure enough, simplification. And this kind of follows logically, but you do need to name it. You got to call it out. If P and Q is true, that means separately P is Q. I'm sorry, P is true, comma, Q is true, right? Individually, they're both true. So I can take statement one, premise one, and use simplification on it. And note how I write this. I say, okay, I'm doing simplification on statement one. And the result of that will be P. Well, now I've got P and I've got R. So I can use a conjunction. The conjunction states that if P is true and Q is true as premises, then I can conclude, therefore, P and Q is a true statement. Well, in this scenario, right, don't let the letters distract you. I've got a premise R that's true, a premise P that's true, so I can make this statement P and R using a conjunction of 2 and 3. And with that, I reach my conclusion. Let's look at a more complicated one. I have 3 premises this time. P implies Q or R implies S. It is not the case that R implies S. Q implies R. I want to reach the conclusion P implies R. Again, let me scoot that out of the way, pull my table over here, and just start looking around for what it is I could possibly get. And in this case, what I'm going to use is actually the disjunctive syllogism. I know that one has to be true. That is that the first implication or that second R implies S implication must be true. But 2 already provides for me the fact that it's not the R implies S that's true. So I can conclude it must in fact be that P implies Q is true. So disjunctive syllogism of statements 1 and 2. So now I'm looking around. I'm still trying to get to P implies R. I can get there with a hypothetical syllogism. That is, if I have P, P gives me Q because it's implied. And then I know that if I have Q, that would give me R. I can jump all the way to the end here. In this case, the letters match up exactly with the statement in the rules for inference, but I get through the hypothetical syllogism, the statement P implies R is also a true statement. So I have reached my conclusion. Another example. Here I have these 3 premises. I'm going to start as before, move my conclusion down out of the way so it's not distracting me. I just want to reach the conclusion P. And just like before, just treat these as a puzzle, right? I have these different roles. I'm just trying to figure out which one I can use, take the pieces, move them around. What do I have? Do they match anything? Here, I'm going to apply modus tollens first. And do note that we've not seen one yet where I can go off the rails. But you can generate a bunch of statements that aren't necessarily going to help you get towards the end goal. So it's possible you get some extraneous stuff from these. I know not R is true, and I know that Q implies R. So using modus tollens, I can conclude not Q using statements 2 and 3. Again, be sure to state the rule that you're using and the 2 premises that you use if it takes 2. Next, I'm going to modus ponens. of 1 and 4. I know not Q is true, and I know that if I had not Q, then I have P. So I can conclude P, and that gets me to my conclusion. One last one here. Sorry, my conclusion is in the wrong place there. Let me go ahead and move that out of the way. So I'm trying to reach the conclusion, therefore R. This time I have 4 premises, and this one's going to be a little longer. I'm going to give you some more techniques that we can use. So first I'm just trying, yeah, I want to get to R, but I'm just looking for anything that I can do here, right? Just get my foot out the door. Where can I start to approach this problem? In this case, what jumps out at me is a disjunctive syllogism. I know that P or S must be true, and I know that it's not P, therefore it must be S that is the true one. And now the next step, it gets a lot trickier. Because where can I go from here? Right, we're looking around, and it's not jumping out at me. So one thing I tend to do, if this is me, is that while yes, we can reuse statements, one tip I have is that to keep track of the statements you have used. In particular, I've generated a new statement, S. If you've done crossword puzzles or Sudokus or anything like that, you know that once you get going in a direction, you try to use the new piece of information, right? If you're just doing a traditional puzzle, when you place that new puzzle piece, you start looking for other pieces that plug in. So is there a way for me to use this S? Well, let's also go ahead and say, well, I've used 1 and 3, and so while I could circle back and use them again, let's for now remove them and say, well, I've already used them. Maybe I can get some more, uh, maybe I can get further along using the unused pieces of information. Again, not to say that I can't use them a second time. So then I'm looking, right, I want to use that S, that new piece of information, and I'm going to decide, well, let me not look at 2 either, because it's got no S's in it. Which leaves me looking at statement 4. And the problem there is that while it has an S, it has an S or a T. Is there anything I can do with that? And there is. I can use addition. Addition tends to be really hard to spot. We'll see this a couple of times throughout the course because we're kind of trained to pare things down and make them smaller and smaller and smaller. But this idea that you can just do whatever you want as long as it's true, right? If you want a or T there, you can tag that on because it doesn't change the truth value statement of S. So I'm going to add the or T there because I want it. I know S is true, and I can say or whatever, and it doesn't change the truth value statement. So I'm going to add that or T on to the true statement S that I already have. Well, now I'm kind of off to the races. My next step's obvious. I'm going to modus ponens 6 and 4. And I can conclude Q. Same trick. I can now add whatever I want. Trying to get to the R. The statement I've not used is statement 2 there, the Q or P. I say, okay, well, again, I can add that or P for free. And now I'm so close. I know that Q or P is true, and I know that if Q or P was true, then I could conclude R. And that's just another application of modus ponens. Okay, so that brings us to rules of inference for quantified statements. And these tend to really trip people up. So let's go over what they are, and then I'll discuss why I think it's difficult to figure out what's going on here. Universal instantiation is the idea that if you're told it's true for everything, then you can pick out a single element and it will also be true. Conceptually, that's not difficult, but as we're going to see when we put it into action, I think the problem is that it's almost so simple that people want to just run over that statement because it's so plainly obvious on its face. So if you said something like all waitresses are females, that's a statement about the population of all, right? Our domain then is all waitresses. So if you pick someone who is a waitress, a single instance of that universal statement, thus universal, or there's where we get the term universal instantiation, you can conclude Lisa is a female because she is part of she's an element in that domain. We can also have universal generalizations. This is the other way around. This is if you're told that P of C is true for all the elements, well, you can generate the new statement and say, well, then for all x, Px is true. There's existential instantiation. That is, if you're told there exists some element that makes the statement true, you can go and give that element a name to be used. In this case, in the case of the definition, we say, oh, well, you can say P of C is true for some element. We're going to call that element C. There is someone who won the lottery. Let's call her C. So we can now say C won the lottery. Existential generalization. Given that P of C is true for a particular element C in the domain, we can generalize that statement and say, well, then there exists someone. Why? We can take their name off of it if we want. Right? You can almost think of this as making that one person anonymous, right? We take their name off it, but we can still say it's true for someone. So Andy won the lottery. That's true. But say Andy doesn't want his name out there. Well, it's still a true statement to say there is someone who won the lottery. So we're finally ready to circle back to this problem we had previously. We want to finally be able to symbolize the logic and convince ourselves that if we know for a fact all men are mortal, and we know for a fact that Socrates is a man, so we have those two as premises, can we now get the conclusion Socrates is immortal? So first we're going to come up with some propositional functions. I'm going to let m of x denote x is a man, and r of x denote x is a mortal. So I can symbolize the two premises. The first one says for all the elements in the domain, m of x would imply r of x. That's the trick there is that it's not making the statement for anyone in particular. It's saying for everyone who is in the domain, right? If they are a man, that would give me that they are mortal. The implication is what it's making a true statement about for all the elements. M of 2 is made, or the second premise is there. That second line, Socrates is a man, is saying the propositional function is true for this one specific instantiated element, that is Socrates. The conclusion we're trying to reach, oh, sorry, that's a typo, is therefore R Socrates. I apologize for the typo there. So that's the conclusion we are trying to get to. Well, we universally instantiate statement 1. That is, if it's true for everyone, it would be true, the implication would be true, for someone named Socrates. So if in fact Socrates was a man, the implication that he is immortal would be a true statement. Well, now it's just a modus ponens away. We, as an assumption, have assumed that Socrates is a man. So the implication holds true from statement 3, giving us our Socrates and giving our conclusion. So I'll walk through a more sophisticated example. Everyone in Illinois has heard of Lincoln. Someone in Illinois has not visited Lincoln's tomb. So, conclusion, someone has heard of Lincoln who has not visited Lincoln's tomb. We're going to need some propositional functions. We're going to let I of x denote x lives in Illinois, h of x denote x has heard of Lincoln, and v of x denote x has visited Lincoln's tomb. Let's symbolize those premises. For everyone, it's true that if you live in Illinois, you've heard of Lincoln. That's the first statement. Finally, the second statement, as far as premises go, says, hey, there is someone in Illinois who has not visited the tomb. The conclusion I'm trying to get is that there exists a person who h of x is true, that is, they have heard of Lincoln, and it is not the case that they have visited the tomb. So let's go ahead and stash that conclusion down below. That's what we're going to try and get to. And we are off to the races. The first thing we're going to do is look at statement 2 here and say, well, there exists someone. Well, let's give that someone a name. Let's existential instantiate statement 2. We'll call this person Sue. So Sue lives in Illinois and has not visited the tomb. Well, now we can universally instantiate statement 1. The implication would hold true that if Sue lived in Illinois, then she would have heard of Lincoln. I can simplify statement 3 and say, okay, well, I know it is true that it is the case that she lives in Illinois and she has not visited the tomb. So I can strip those two apart and say, okay, well, independently, I can just say Sue lives in Illinois. Now I can apply modus ponens and say, well, Sue lives in Illinois, and I also know that it's the case that if Sue lived in Illinois, then she would have heard of Lincoln. So I get that Sue has heard of Lincoln. I'm almost there. Looking at my conclusion now, I have that Sue has heard of Lincoln. I'm also going to need that she has not visited the tomb. Again, I simplify 3 and take that part away. So now I'm ready to conjunction. I've now got this person. I've named her Sue. She has heard of Lincoln and not visited the tomb. Here's the problem, though. I don't know that this person's name was Sue. It was this hypothetical person that we made up. So at the end, we're going to generalize the statement, right? Sue, you could go through this argument and you could replace Sue with any name because it was kind of just like a variable, a placeholder to construct this argument. So at the end, I generalize the statement back the other way. And so I think where this goes wrong, I want to go ahead and mention this when people are working on this section, is that they try to treat X as a variable name, as Sue, but typically use X and Y and things like that when we're talking about variables that are bound with one of those quantifiers. So when you're going to, in particular, instantiate, I suggest you get away from those simple single letter names, right? This would be a lot harder to read if I decided to name Sue X, because then this whole thing would just have X's running around. So if you can, give it a more descriptive name when you instantiate. And finally, I want to leave you off with trying this one. So go ahead and pause the video, give it a shot. I'm going to drone on here for just a second longer, giving you a chance to pause it. See if you can figure this one out. Everyone who swims every day is fit. Alex is not fit, so Alex does not swim every day. 3, 2, 1. This is the solution that I get. You do need to create propositional functions to draw that conclusion.